Hi, my name is Sammy Hasten, and this is my Lab 5 report on Faraday's Law. Here's a brief overview of this presentation. I will start with the purpose, followed by the physics principles used, the procedure, measurements, computational model, results, and then I'll finish with my conclusion. The purpose of this lab was to use Faraday's law to relate magnetic field of a falling bar in a magnet with respect to time to a Curly electric field around an aluminum tube. The aluminum tube produces a current, and we see that the aluminum tube current produces a magnetic field which exerts a force on the source of the B external. It is important to note that the aluminum tube is somewhat representative of a solenoid. There were four main physics principles present in this lab. The first one was Newton's second law, which is just F equals ma. F represents force equals mass times acceleration. And then Faraday's law, which is magnetic flux linking a circuit changes, electromotive force is induced in the circuit proportional to the rate of the change of the flux linkage. Another law was Lenz's law, which is EMF equals the negative change in influx magnitude over change in time. And the last physics principle used was Newton's third law, which is just FB on A is FA on B, so there's an equal and opposite reaction for a force. The procedure for the lab began with creating an aluminum tube at the desired height. The height was just the roll itself. We dropped a bar magnet through the aluminum tube acting as a solenoid, and then we recorded the time it takes for the bar magnet to fall through the tube. Once we had this, we repeated it 5 times, and with all those times we got the average time, which is what we use as our experimental point. The measurements for my tube were the tube length of 0.3 meters and the radius of the tube was 0.017 meters. For the data points, I had 1 second, 0.98 seconds, 1.3 seconds, 1.6 seconds, and 0.9 seconds, and the average of all those was 1.16 seconds. Pictured here is the computational model for the Lab 5 presentation. You can see the graph for how the velocity changes over time for the bar magnet falling through the aluminum tube in our glow script model. It took the magnet 1.353 seconds to fall through the 0.3 meter tube on the computational model. And to the right, you can see the piece of the code where you calculate the time it takes to go through that model. I calculated my results for this lab, the time to pass through the aluminum tube experimentally, and this was when I did it myself, and I got 1.16 seconds as that average time, as well as the time to pass through the aluminum tube computational model, which is what we just went over in the previous slide, and that took 1.35 seconds. So here I calculated percent error. I'm not sure if this was necessary, but I said that the computational model was the expected value, and then the observed model, or the experimental model was the observed, and I got 14.1% error from the experimental to the computational model. And in conclusion, we have to answer 2 questions. The first one is, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the falling magnet would be slower as the current would be larger and the magnetic force from the aluminum tube would be greater. And then what if the holes or the slots were cut into the tube? How would this affect the ring current in your model? So if this were to occur, the resistance would increase because there would be a smaller number of complete rings. And this concludes my Lab 5 presentation. If you have any questions, please feel free to reach out, and attached in the link will be my glow script code. Thank you so much.